Where so today we're welcoming Dr. Yuzuru Kanda to our Trant Lab group meeting, where he's going to discuss some work that he did during his PhD with Baran at the Scripps Research Institute. And his talk is entitled Two-Phase Synthesis of Taxol. And my understanding is this is a global first of this presentation, so we're super excited to see this. So Dr. Kanda, take it away.
Cool. You guys can hear me here now?
Sorry?
Do you hear me?
Yeah, we can hear you. I'm just going to turn off my microphone. Please pause.
Cool. Thank you very much for the invitation and this opportunity, also accommodating my schedule in the last minute. And sure how you guys take any questions at the moment or at the end or
the problem is from Dr. Kanda's microphone.
Yeah, Dr. Kanda, we're having trouble with the microphone, and I'm not sure what it is, but it was really kind of poppy, and now it's not silent again. So do you have another microphone you can use? Or do you only have to get away with one microphone? It seems to be a little bit tricky. I don't know if you're speaking, I can't hear you.
Hello?
Hello, I can hear you now.
Okay, is it still choppy?
No, I don't.
Sorry, yeah, no, we lost your microphone there. It was maybe really poppy and it wasn't very clear. So I think that as Dr. Banerjee is saying, it seems to be quite a bit better right now. So start from the top again. I'm sorry.
Okay, no, sorry. Yeah, I think it's my issue. Yeah, let me know whenever when the audio or the image gets a little weird or choppy.
I will.
Cool. Yeah, let me then we go further today. So yeah, I'm gonna talk about the two-phase synthesis of Taxol I worked on during my PhD. And before going into the detail, let me briefly talk about myself because probably none of you guys know about me. So I'm originally from Japan. I did my undergrad study at the University of Tokyo under supervision of Eiichi Nakamura, where I studied the facile electron transfer between this rigid donor and the acceptor system. And I moved to US 2015, and I was in the field lab and worked on 3 different oral synthesis projects: pterosidin and Taxol and the vitamin D. And 2020, I joined the MIT Professor Alex Lusovic lab, and I mainly worked on phosphate catalyzed nitroalkane cross-coupling reaction with formic acid, as well as printogen-based SS bond oxidative addition project for the ADC trying to application for the antibody drug conjugate. And now I work at the Novartis Institute for Biomedical Research as a medicinal chemist. Besides the actual chemistry, I own the chemistry jewelry brand, and I used to sell those jewelry back in Japan. I got too busy for chemistry during my grad school and postdoc, but now I have a little more time and money to do this kind of stuff again. So I might start selling those in US in the future. So because you guys are really interested in the Taxol two-phase synthesis, I will focus on this project for this talk. But if you have any questions on other projects, I'm more than happy to discuss later. So there have been 11 Taxol synthesis reported so far. Then you will obviously ask the question, why do we need another Taxol synthesis in the 21st century? And let me try to rationalize that. To begin with, let's talk about the complexity of the molecule. So here's a formula that represents the complexity of the molecule, which is formulated by chemist at BMS. They attempted to quantify the complexity as a sum of 2 terms. The first one is intrinsic complexity. It's constant value that represents the innate complexity of the molecule, such as the number of heterocycles, number of coronary center, and so on. And the second term, extrinsic complexity, is a time-dependent variable that decreases as more powerful synthetic methods are invented. So for example, cross-coupling reaction certainly contributed to decreasing the extrinsic complexity, particularly for the drug discovery and the process chemistry. The development of cross-coupling reaction affected our view towards the synthesis and provided us with the new synthetic strategies. For the drug discovery perspective, the divergent approach is the most sensible strategy to maximize the speed and the output of the structure-activity relationship analysis. Even then, the complex natural product is still not the readily attainable target for the purely synthetic analog exploration for drug discovery. The major objective of this Taxol project is trying to examine the assumption. So our question was, could a complex terpene represent a viable starting point for the medicinal chemistry campaign in the absence of semisynthesis? Oh, do you guys hear me okay?
Everything is good.
Okay, good. Okay, just checking. Cool. All right, and then namely, disconnect the target terpene into a naked carbon skeleton by a series of CH oxidation events called oxidase phase, as if medicinal chemists cross-coupled their design side chain into the parent skeleton, and synthesize the low oxidation level core from the commodity material. Theoretically, this two-phase approach allows us to carry out a comprehensive oxidation level fingerprint screening for the entire natural product family. Admittedly, this project probably would not be a practical drug discovery campaign, but I would consider it as a thought experiment with a little bit of chemistry exercise that could provide a blueprint for this kind of natural product-based drug discovery project. In past, Liu Pharma funded our lab for two-phase synthesis of phobo, ingenol, and toxicurgan. I believe all those syntheses provided the partial proposition for this whole question, but we'd like to conclude this whole two-phase project by completing the most tensely functional terpene, the Taxol. So let me quickly give you an overview of 13 years of Taxol journey. Yeah, this project took 13 years for the Baran lab to complete, and I'm not the one that was there for 13 years. I was just joined the lab and worked on the project just as the right timing. So I was the last person. I happened to be the last person to finish the project. So in 2007, the field ambitioned to carry out the biomedic terpene synthesis using a CH maximization. And Yoshi and Abraham bravely took this initiative in the project and literally started from scratch with no data. In 5 years, they established a practical and scalable cyclase phase. And the project was handed over to Nathan, Mine, and Abraham, and they established 3 different residual selective allelic population on a taxane core and achieved the first two-phase synthesis of taxane natural product. They also discovered the synthetic utility of chromium-5 reagent, which is nowadays widely used for a variety of natural product synthesis. So after the proof of concept, Chansha, Yefa, and Nathan targeted the taxane at the even higher oxidation level. They established a robust method to function as a middle B ring. And that was about the time I joined the lab and took over the project with Shige. We went through a lot of unsuccessful attempts in the first few years. In 2018, we were joined by the excellent collaborator, Kanda. They bravely undertook a cyclase phase scale-up and significantly improved the protocol. In total, they prepared more than 100 grams of enantiomer pure cyclase phase end product for us. And he joined the project in last year to wrap up the whole synthesis. So based on those histories, our 4 major tasks left for us are those 4. The first one is C1 oxidation, which is the bridgehead position, and the next one is C7 oxidation, which is next to coronary center. And I'd like to note that both of them are sp3-CH oxidation, unlike the allelic for alpha oxidation those are order of magnitude more challenging. And third, we need to figure out the oxidation choreography. There are so many functional groups that is in the Taxol, but we need to determine what is the best way and best order to install those oxidation.
Silent. We can't hear you.
Lost you there, Kanda. Can you hear us? Okay. Here again. So what I'm going to do actually is I am going to mute. And Dr. Kanda, we lost you there for a moment, so I'm sorry I removed you waiting.
Do you hear me all right?
Yeah, I can hear you now, yes.
Okay, cool.
So
Where did it
just before the slide, we'll go back slide.
go back slide? Here?
Yes, I think this is where we lost you. We had just finished
Okay.
a history lesson on the project in the Baran group, so I think this is where we are.
Okay, okay. Yeah, so sorry. Do you guys hear me okay?
Yeah, I can hear you.
Okay,
Yes.
yeah. So if you're interested in the reactions or substrates routes I'm not going to talk about today, you can find those in the SI or the JOC perspective we published. So let's dive into the Taxol synthesis. And before moving on, I would like to acknowledge again the work done by Kanda. They significantly improved our cyclase phase, which is our lifeline to export our oxidase attempts. They shaved off one step from the previous routes and established an easy, safe, cheap, and reproducible, very robust route to provide NMP pure material by exploring the new ligands and trying different conditions, different disconnections, and everything. So I'd like to acknowledge their hard work and the creativity, and they provided more than 100 grams of NMP pure taxodione material for us. So first thing I want to talk about in the oxidation phase is this early stage oxidation choreography. So it might make more sense to introduce more difficult hydroxy groups such as C1 and C7, but the ultimate goal of this whole project is providing a proof of concept of taxane-based analog preparation. And we know that C13 side chain is necessary for bioactivity. So we decided to carry out this oxidation first. The chromium 5 reagent I previously showed you here, they provided us with this radioactive C13 oxidation product. Despite the presence of two more allylic positions, this chromium 5 reagent successfully hit the desired position in an exotic combination of solvent, HFIP, and trimethylcyanol. The solvents previously used for this transformation, such as trichloroethylene, acetonitrile, wasn't very effective and provided us with no reaction or radioisomers. Site-selective C5 oxidation was achieved using copper-2 bromide as an oxidant, and there are 3 ketones and 5 mineralizable positions in the substrate, but the kinetically most mineralizable carbon was selectively brominated. the use of bromine as an oxidation state placeholder obviated the need for protecting group. It also played a pivotal role in the following C10 oxidation. So the C10 oxidation selectivity represented how conformationally sensitive these taxanes are. For this particular substrate, the desired product was obtained as a single radioisomer. However, substrates with other substitution patterns, protecting groups, and oxidation levels gave a mixture of radioisomer or decomposition, which is a good example illustrating the functional group on the one side of the molecule could affect the reactivity of the other side of the molecule. A potential reason for this excellent radioactivity is the serine conformation changed upon heating to put the large bromo group in the pseudo-equatorial conformation. This rendered the C10CH antibonding orbital well aligned with this pi orbital for the bridgehead of the bridgehead olefin. Interestingly, those C5, 10, 13 oxidation were also carried out in the early stage in our previous two-phase approach with low oxidation state taxanes. It is also noteworthy that similar oxidation order is known for the biosynthesis. So we happen to find a coherence in the chemical synthesis and the biosynthesis. So in summary, we achieved early stage oxidations in the perfect radial selectivity despite the presence of many oxidizable CH bonds in the molecule. We also minimized the number of protecting groups, which shaved off the many steps from our total synthesis and maximized the material throughput. And I would like to emphasize more that the oxidation choreography was analogous to our previous two taxane natural product synthesis as well as biosynthesis. So next, let's talk about one of the key steps in our synthesis, the C1 CH oxidation. So C1 oxidation is one of the most challenging steps for us. This bridgehead position is quite hindered, and it is known that generation of either cation or radical at this position triggers skeletal rearrangement. So we have to be very careful and selective for conditions. So we took advantage of this CH bond close to this C2 functionalities. And we examined a number of directing groups taking advantage of this ketone or alcohol. However, it turned out that C2 position is extremely hindered that even putting a directing group was challenging. Here I'm showing some compound that we could actually synthesize, but long story short, no C1 oxidation was observed. Another potential reason for the failure of directed oxidation approach was that the active oxidizing species were too close to the target CH bond that they might not be able to adopt the right configuration to react with CH bond. One interesting result from Breslov-Dubois type 19 insertion, this was the only successful directed CH oxidation attempt. However, this carbamate was really robust and we couldn't deprotect under any conditions. So we finally abandoned this oxidation success. To briefly summarize, we abandoned directed C1 oxidation approach because of the sterics to C2 and C1 position. And we also often observed the reaction at the bridgehead olefin at C11 and 12, probably due to the high electron density and which led to the substrate decomposition or undesired oxidation. So here we switched back to the intermolecular CH oxidation approach. The encouraging news is that there's actually a report by Oritani group. They subjected this advanced taxane intermediate to DMDO and achieved the C1 oxidation in a really high yield. If that works for us, of course not. We subjected a variety of taxane intermediate we had. We tried different oxidation state, different oxidation pattern, different protecting groups and everything, but we never observed the C1 oxidation product. So we started wondering why, and the problem becomes more obvious when the structure is drawn in 3D. If you draw in 2D, the Taxol looks really flat, but it's actually not flat at all. It has a really caged and interesting structure, which attracted other chemists in the history. So by drawing in 3D, the C2 alcohol is actually really close to C1 CH bond. So we start to wonder this beta C2 alcohol alpha C2 alcohol is strictly or electronically hindering the C1 oxidation to happen. So we prepare this C2 unnatural alcohol to remove sterics around the C1. And subjecting this compound to DMDO, luckily we could observe this desired C1 oxidation product in a trace yield, accompanying this undesired C2 oxidation product. So the problem is very obvious, competitive oxidation at C2. But as you can see in the 3D structure, the C2 alcohol is extremely hindered, and we try to put any kinds of protecting group, but nothing really worked. So we started wondering what is the small protecting group that could be put on this extremely hindered alcohol and suppress the undesired oxidation happening at the C2. And the conclusion we got was this deuterium approach. So this C2 detaxane undergoes desired C1 oxidation at 20% yield. Sure, it's low yield, but it was much, much higher compared to the trace yield and allowed us to explore the downstream chemistry thanks to this deuterium approach. In the course of examining the substrate generality of this C1 oxidation, it turned out that this reaction is extremely sensitive to stereoelectronics around C1. So C4 position has to be tetrasubstituted, otherwise instantaneous C2 oxidation was observed. And here's another case, a functional group on the one side affecting the other side of the molecule. So in the absence C5 substituent, C13 enone formation was really took place really rapidly. When C10 OTES resides in the opposite alpha stereochemistry, it sits in the axial conformation despite the large A values. Then the bridgehead olefin was exposed to DMDO, and only the epoxidation at the C11-12 position was observed. So after extensive conformational analysis and substrate screening, the substrate shown here was discovered to be optimal substrate for C1 oxidation. Functional groups in the hierarchy in orange are repurposable for the downstream functional group interconversion and serves as the essential protecting group to carry out C1 oxidation in a chemo and a selective manner. Subjecting this compound to DMDO, we got 25% yield of desired compound A, accompanying intermediate B, as well as the undesired oxidation product C. So, oops. All right, so 25% is not terrible, but it is still the mid stage of the synthesis, so it would be ideal if the material throughput could be improved furthermore. However, there is virtually no modification for DMDO oxidation, and C1 oxidation was just simply too slow that starting material and
Anyways.
oh, you guys hear me all right?
Yes.
Yes.
Okay. Cool. Yeah, so during the reaction, the DMDO was just too harsh for this taxane skeleton, and we started seeing material degradation if the reaction time was extended. So in order to enhance the reactivity of DMDO, as well as increasing the reaction rate, we decided to extract the DMDO of the other solvents. And it turned out that chloroform was particularly effective, potentially due to the hydrogen bonding of chloroform and the DMDO, which enhanced the DMDO's reactivity. Even higher concentration DMDO allowed the reaction to be completed at 0 degrees. And it is noteworthy that amount of unreacted material B was decreased to only 8%, which significantly reduced the rate of recovering B and resubjecting to DMDO. And here's some pictures of the preparing DMDO on large scale in the lab. And this is the 20-liter flask, which was unfortunately the largest flask we could find in the lab. This could be charged with 1 kilogram of oxygen for one run, and it produced about 300–400 ml of DMDO acetone solution, which could be stored in a 3-liter flask here and there, like this in the freezer. And this acetone DMDO solution was transferred this ice-cooled set funnel and quickly extracted to chloroform to get the chloroform acetone DMDO mixture, which was further washed with phosphate buffer to get rid of excess acetone and increase the concentration of chloroform DMDO solution. So in summary, we could achieve C1 oxidation in extremely high chemo-regio and stereospecific fashion. And we could take advantage of all the functional groups in the substrate and maximize the material throughput and shapes of the unnecessary protecting group manipulations. Kinetic isotope effect and the choice of solvents and concentration significantly increase the reaction yield and achieve this whole synthesis possible. All right, so now the C1 oxidation worked, but C2 need to be like deprotected, meaning that getting rid of deuterium and flicking the C2 stereochemistry back to the natural form. So the oxidation of C2 worked just smoothly with TPAP NMO. And the next C2 reduction is not straightforward. First of all, the C2 position is extremely hindered that it didn't even react with typical reduction conditions such as LH. And to make it worse, the backside of C2 ketone is completely blocked. So unsurprisingly, the most reduction condition gave either no reaction or undesired C2 beta diastereomer. And dissolving metal single electron reduction is typical tactic to leverage unreactive hindered ketone like this. However, those conditions are typically basic, and this hidden keto alcohol undergo retroaldol reaction followed by recomposition. So this significantly limited possible reaction conditions and substrates, which ended up making us reroute the whole synthesis 3 times. Phil also acknowledged that this is the most ridiculous ketone reduction he's ever seen. So long story short, after careful conventional analysis and rerouting, we successfully identified a substrate that gave the desired diastereomer. We hypothesized that this C4 beta stereochemistry and the C5-6 epoxide prevent a retroaldol reaction to happen. And under bottom-up blank type reduction condition, the resulting radical intermediate prefers to sit in a gauche conformation and afford the desired alpha hydroxy group at C2 position. So C2 reduction proceeds in the high stereoselectivity fashion without touching the epoxide and other functional groups in the molecule. Extensive conformational analysis was necessary to design a substrate that gives the desired diastereomer by overcoming the innate steric issues. So next up is the key CH oxidation, C7 oxidation. So we initially examined directive CH oxidation by taking the advantage of this 1:3 relationship between C7 and 9. Even though a number of directing groups were examined, it was extremely difficult to put the directing group at the C9 position. And to make it worse, the analogous to directive C1 oxidation approach scenario, C7 was too hindered that it didn't undergo any reactions. This breakthrough Devore type 19 insertion chemistry illustrates how sterically congested C7 is. It went for C19 despite the electronic preference for the methylene. So we attempted to leverage the reactivity of C7 by converting it to allylic CH. Virtually all existing allylic oxidation methods were examined. However, nothing really touched the C7 position. Then we tried to pump up the electron density at the C7 furthermore by converting it to binding gas inert ether. And the Sigusa oxidation of double binding gas inert ether for the C7, 9, 10 triple oxidation product. However, the C9, 10 olefin was too hindered and it didn't undergo any further functionalization. Then we gave up on C9 oxidation and went after direct bis hydroxylation at C7 and 10. Treatment of this binding gas inert ether with singular oxygen followed by DMS for the C7-10 diol. However, this compound has several issues. The first, C7 stereochemistry is wrong. And second, the C10 stereochemistry is also not ideal. I mentioned this earlier, that the alpha hydroxy group cannot protect the bridgehead olefin from DMDO oxidation. And the third, there are no suitable protecting group for C7. The installation of too many similar functional groups in the early stage of molecule cause the protecting group manipulation issues, which is particularly big problem for taxane because pretty much all functional groups in the molecule are secondary alcohol and they are really close to each other. Therefore, it is critical to consider oxidation choreography and in so many functional groups as synthetic equivalent by which we could avoid the protecting group manipulation issues and we can differentiate them when needed. So therefore, the oxidation relay was adopted to circumvent those issues. This epoxide A was subjected to TBAI and BF3 ethylate to give this iodohydrin B. As you can imagine, this is very unstable and it could go back to the corresponding epoxide A. So it has to be protected in situ under really mild condition. So we use the TMS imidazole to convert it to protected alcohol, compound C. However, it seems that leftover Lewis acid in the reaction caused some protecting group scrambling at the C10 position, and we observed the C10 TMS test mixture, which were not separable by PTLC. So we looked for quencher for those Lewis acid, but we need to choose a Lewis base that is strong enough to quench the leftover Lewis acid, but not too strong to induce the epoxide reclosure. At the end, we identified this 2,4-pyridine has a perfect basicity that is not too strong to cause the epoxide reclosure, but enough to quench the leftover BF3 ethylate and Lewis acid. This alkyl iodide was subjected to DMDO, which formed this iodophile species that undergoes rapid zinc elimination to afford olefin, which was further converted to epoxide with DMDO. And the inflowment of C7 hydroxy group was finalized with using this Nugent-Rajan Babu reagent in presence of triacylsilane, which increased the reaction yield significantly. And our group was actually the first one that reported the combination of this Nugent-Rajan Babu reagent and the triacylsilane. And it seems this condition was somewhat general because it was immediately utilized by the Graham-Macreasio group in the synthesis of anhydrous ryanodol. So in summary, C7 oxidation was achieved by oxidation relay. This oxidation proceeded with a high chemo and stress activity without ruining sensitive functional groups in the molecule. C7 hydroxy groups were introduced indirectly by interconverting non-hydroxy groups. Such redundancy could be a weakness of two-phase approach. However, especially for densely functionalized molecule like Taxol, deep consideration of oxidation choreography and indirect approach was critical to for the overall efficiency of the whole synthesis. And the end game is similar to Houghton's approach, so I will not go through one by one, but each step has some issues and some dramas and stories, so I'm more than happy to discuss in detail if you have any questions. So in summary, inspired by the medicinal chemical retrosynthesis and biosynthesis, we succeeded in the two-phase synthesis of Taxol by developing a series of site-selective oxidation methods. I have to acknowledge that it is nothing more than an academic exercise and too far from practical medchem, but at least I believe that this 13 years of effort at least demonstrated the feasibility of devising a unified strategy for divergent synthesis of complex helping molecules. At the end, but not least, I would like to thank Phil, the advisor who literally funded this project out of his pocket, and the great collaborator and co-worker Shige, Hugh, and Kambida. I couldn't talk about chemistry done by Kambida, but they did an excellent job fixing all the issue with starting material preparations and delivered us a lot of inactive film material and did all the heavy lifting work. I also want to thank the funding sources and the fellowships, and thank you very much for attention, and happy to take any questions.
I don't know if you could hear that. I don't know how good my microphone is. any questions in the chat?
Sergey is raising his hand.
I don't see any questions in the chat for now. Please let me know if
I muted myself, so I'm just going to unmute myself.
yeah, I can hear you.
John, someone is raising his hand. Sergey?
Okay, there we go. Okay, so I'm unmuted now, so that's good. Sorry, okay, so we have a question from Sergey Vishenko. Sergey, go ahead.
Hi, thank you for talk. Very nice talk. I have, I guess, major question of total synthesis chemist. How did you guys do material management? So you have 100 gram of advanced intermediate which was made, right? How did you guys try it, and when you decide to, to push forward? This is conditions is good enough. Let's make a 2 gram push to next step.
Yeah, that's really good question, and I learned that by doing the synthesis, and there's no like golden rule for that. But one thing that was really helpful for us was that Scripps has an excellent NMR facility. So I was actually doing 25 microgram scale reaction for the front line. And if that works, I'll scale up to 100 micrograms. And if that works, I will scale up to 1 mg, something like that. But I will say the major issues we got stuck was C1 oxidation and C2 reduction. So we bring the material all the way forward right before the C1 oxidation and examine a lot, and and then try a bunch of conditions for the reduction, stuff like that. And afterwards, the other chemistry after C2 reduction was relatively straightforward for me. So I didn't have to really worry about going with 25 microgram scale reactions and something. But yeah, that's how we manage the material. But yeah, it was really nerve-wracking scaling up the reaction. If that may get messed up, we will not have anything to work with. And I have to confess that I sometimes messed up the scale up, but Phil was never upset. So yeah.
How do you weigh 25 microgram? Do you have a robot to do it?
No. Just make a stock solution.
Oh, I see. Yeah, makes sense.
Yeah, and also like on that scale, it doesn't really matter how much material do you have. Like as long as I can take TLC or maybe an ML, then it's all good.
25 microgram was your probe scale.
Yeah.
That's insane. Okay. Cool. So like your reaction better go basically to completion for that to work, okay?
Mm-hmm. Oh, sorry.
It has to be pretty clean because you really can't clean up 25 micrograms very easily.
Yeah. I mean, if reaction is clean, great. If reaction was messy, I will scale it up to 100 micrograms. But thankfully, taxanes, all taxane intermediates are really it stains really well with anisaldehyde, and so we rarely miss any byproducts from the reaction.
Part of your answer there, because I think your microphone was playing up a little bit, but I think I caught that you were sort of doing a lot of it by TLC and LCMS.
Oh, right. Yeah. We can use LCMS. It doesn't really ionize well, and Baran Lab doesn't really have a functional LCMS. So I was living up on pretty much only on TLC and NML.
Feel a little bit better to know that the Baran Lab didn't have a functional LCMS. Okay, any other questions from anyone else in the audience?
I see
in the chat, and I'll just pass these on. Yeah. So
I have a quick question from computational perspective.
Sure, go ahead.
I'm just wondering, do you use any computational study, or do you have any someone in your group to assist with the synthesis using computational techniques?
Unfortunately not. That's, yeah, we wish there's someone who helps us with computations. We try to, it's not quite a computation, but we try to predict the reactivity of C1 oxidation by quantifying the carbon and proton chemical shift at the C1 position. But that didn't really translate it into the reactivity of our substrate. But yeah, so we didn't really do use any computational tools.
Okay, thank you.
A couple of questions. Is this route appropriate for the preparation of any paclitaxel derivatives? And then she asked her, what do you mean by oxidation choreography? And what does the two-phase mean? Like, how do you organize the two-phase synthesis? So
Okay, so the first question, yeah, first question, in theory, yes, because as I said, we install the 13 oxidation state first, so we can put in, just reduce the ketone, put the side chain, and it's taxane analog. But are they bioactive? Probably not. And is this a really right, easy way to make a bunch of taxane analogs? Probably not. Like, you can do it, but it's gonna be a lot of heavy lifting. And I think best way to approach this kind of stuff will be the combination of enzymatic approach plus sometimes chemical approach. Like, it's really, the enzymes are really powerful to hit the CH bond at the middle of nowhere. And also making the taxane skeleton, the enzymatic approach is much, much cheaper and faster. So yeah, that's my answer for the question one. And question two, what's the oxidation choreography? Yeah, this is a little fancy term field likes to use, but the oxidation choreography, we basically mean the order and the way of doing oxidation. I mentioned during the presentation, but there's too many similar functional groups, secondary alcohols or ketones in this case. So we have to very careful which oxidations are installed in when, in what form. It could be hydroxy group, it could be ketone, it could be olefin, it could be halogen, anything. So we combining all those, we just call it the oxidation choreography. And third question, don't understand much what the two-phase means. Yeah, so easy way of interpreting this is biomimetic terpene synthesis. We construct the carbon skeleton first. This is cyclase phase, and we decolorate that cyclase phase material using CH functionalization, which is called oxidase phase. And the synthesis is split into the cyclase phase and oxidase phase. So those two phases represent the whole synthesis. That's what the two phase means. Did that answer the question?
Basically, yeah, making all the carbocycle skeleton first, because it was really low oxidation state. Right. When you finish the skeleton, then you introduce the oxygens. This is a ridiculously complex project you took on here. Like I have a question I'm going to ask just because of the privilege. There was a lot of model systems that you were carrying through. You're showing examples when you were trying to oxidize specific sites, when the other sites weren't at the oxidation state that they were in your synthesis. How did you sort of consider whether it would still hold true? Like, if you wouldn't have, because there's so many minor changes, like you have a hydrogen for deuterium substitution, and that suddenly switches your reaction stereoselectivity completely. So I can imagine any changes anywhere else in the molecule would have humongous effects, but you are working a lot with model systems for all those oxidations. So how challenging was it to take the model into reality?
Yes, yeah, that's a very good point. And I think it was Danishevsky, I could be wrong, but I said the best model substrate and only reliable model substrate is enantiomer, which I think is very true, especially for this kind of system. Yeah, as you mentioned, we use some model substrates because it's just so wasteful to push the material forward and then try the key reaction and fail. And so we just had to take the model approach, even though it was not desirable. And there are often the cases that it worked in the model, but didn't work in advanced substrate. But also there's a situation that from the reactivity we learned, we sometimes saw the situation where model would not work. We didn't try, but we knew that model would not work. We have to try an advanced substrate. So for example, I will show you. So for example, a C1 oxidation, we use DMDO to oxidate this position. But as mentioned, this brittle olefin sometimes reacts with DMDO. So we knew that we have to install this C13 ketone and the C10 group, C10 hydroxy group to protect this brittle olefin. So there's no point trying the DMDO oxidation with this model substrate because the brittle olefin will just react and that would be end. The C1 loses the reactivity when the brittle olefin is oxidized. So that's the case that we shouldn't use the model. But yeah, going back to the original questions, yes, there are a lot of struggles and unpredictability of using the model.
Question, which I think really plays on some of the other questions that have come up, where there's kind of an admission that this is not a feasible route to create analogs of Taxol. So it's a great scaffold though to learn. And his question was, what are the significant things that you learned during the synthesis in terms of basic synthetic chemistry? What are the biggest takeaways you think for the synthetic chemistry community from this monumental effort?
Yeah, that's very interesting question. I don't know if I call myself as a proper synthetic chemist. Like I have experienced this one synthesis which has basically no nitrogens and all carbon and hydroxy groups. So, but what I learned from here is the first question someone asked, material management. I think that was really important thing that everyone should acquire if we ever work in a relatively long synthesis. And I also learned that desperation is sometimes the matter of invention. I have to go really deep dive in the literature, otherwise I didn't find the DMDO extraction procedure, for example. So yeah, I basically set up the Reaxis search really general and shows 100 pages and go through one by one, hoping that some of them is worth trying. And then, willingness to try making some fancy directing group that probably will not work for our system. But sometimes you have to try. And those willingness, and then your synthetic skill probably follow that, builds up as you make more variety of synthesis.
Just avoiding nitrogens just wise instead of not meaning that you're not a real synthetic chemist. But for an individual reaction, what do you think is the biggest contribution you have made to the art of synthetic chemistry and the art of organic chemistry with the work you've done? What's your proudest achievement from the synthesis?
You mean for the broader sense to the synthetic chemistry, which one will be the most useful reaction, you mean?
One is, what are you proudest of? And what is, you think, the most useful reaction? Those might not be the same. They probably aren't, because that's not the way it works.
Right. Yeah, that's an interesting question. Well, I think this chromium 5 oxidation is already utilized and could be most useful for the useful reaction. Because allylic oxidation there are many reactions reported, but still many of them are too harsh or too dirty and doesn't work really well. So I was actually really kind of interested in following up on this chromium 5 oxidation. I was really curious why I saw very synergy effect in the presence of HFYP and trimethylcyanol. There's certainly something there. And the reaction was extremely clean. Like if you throw this compound with like chromium trioxide, which is the typical allylic oxidation reagent, it's just a barcode on the TLC. But the chromium 5 is just spot to spot basically. So I think those could be the most useful reaction, even though I didn't discover this reaction. The Nathan and the Mine, Abraham, those are the ones discovered this reaction. So the credit for them. And sorry, what was the interesting reaction you said?
Proud of, like, what's your
Proud of?
your masterwork
Yeah.
in the synthesis?
I guess DMD oxidation is certainly I'm proud of, but like this reduction, it looks really simple on the paper.
You muted yourself. There, I can hear you.
Oh, okay, cool. Yeah, I'm proud of this DMD oxidation because this is, fastest, I think one of the fastest steps in the synthesis. But like this C2 reduction, which I'm actually really proud of because it looks so easy on the paper, but it was really, really challenging to find the right condition and right substrate. I have to just look at the plastic model for like days, weeks to figure out what could go on in the reaction. And this is actually the only step I use the model substrate, and that reactivity translated into the actual substrate.
Okay, that's yeah, that's a great answer. That deuterium, looking at trying to use deuterium as an alternative to hydrogen to correct a reaction that wasn't working with hydrogen would never occur to me to try and flip selectivity.
Yeah, it's funny
that's a desperate move, and
yeah.
And then
Yeah,
the sodium reduction. Yeah, that's cool. Congratulations.
Thank you.
Okay, if there are no other questions from the audience, there's one in the chat. Oh, sorry. Yes, Dina is reminding me that she has asked a question in the chat that I did not ask. So she's wondering about your epoxide opening step when you use tetrabutylammonium iodide and BF3 etherate. She's wondering how easy it was to open that epoxide, and she's curious because it looked pretty hindered. And I agree with her, it looks pretty hindered.
Yeah, that's fair. And yeah, it was actually, so BF3 etherate, this condition was the first thing I tried and it worked in the first try. So I actually didn't struggle much, but for the sake of, I don't know, optimization or whatever, I tried other conditions like nucleophilic epoxidation opening never worked. Probably because, what was that? Like here, like if epoxide is opening nucleophilically, your nucleophile approach either from here or here. And either side is extremely hindered. Like you have a coronary center here, and this is tetrasubstitute carbon. So like nucleophilic approach wouldn't work. In that sense, it's really hard to open. But the Lewis acidic approach worked okay. Yeah, as you are right, this C5-6 epoxide is kind of in the concave phase and relatively hindered. But I guess the lone pair, one of the lone pair is sticking outside of the molecule. So I think the BF3 could successfully catch that and leverage the reactivity.
Struggling with some hindered epoxides, and so I think she's hoping for insight.
Oh, I
okay.
see. Yeah.
Autocorrect. So if we don't have any other questions, I want to thank everyone else for attending today. This will be posted live and we'll be sharing this, and thank you. Have a wonderful
thank you very much,
everybody, and take care.
Thank you very much invitation. Appreciate, enjoy talking with you.
Yeah, absolutely wonderful. Thank you very much. I am going to end this session, and my group, we're going to revert to our normal group meeting session for our internal business. So thank you very much. Take care, everyone. Bye.
All right. Take care. Bye.